Hey everyone, good afternoon. Can you guys see me and hear me and see my slides? Wonderful.
Yeah.
Thank you. Perfect. Okay, I've got a couple of super quick announcements. The first is that I will be having extended office hours today from 2:30 to 4:30. So normally I'm available from 3 to 4, but I opened it up a little before and a little after. And I will be online at the typical Zoom link for office hours. I will also be in person in my office. So just bear with me if you come on the Zoom. It's a little bit awkward to do both at once, but just bear with me and we'll just kind of take it as it comes. A couple of reminders for you guys. On Friday, you do have your Achieve Chapter 7 homework due at 9 a.m. on Friday morning. And also we're going to be having a quiz on Chapter 7 in class on Friday. I will email everyone a reminder about this, but the way I'd like to do it is similar to, actually, I'm just going to email everybody about how to do this, whether it'll be the first half or the second half of class, but we will be lecturing for the other half of class. So I get you guys for the whole 50 minutes, part quiz and part lecture. And then I'll be posting an Achieve homework for Chapter 8 coming soon, probably on Friday. So today, what I want to do is touch base with you guys about the tail end of the topic that we didn't quite get to finishing off on Wednesday. Don't worry, this won't be on your quiz. It's really just to kind of make connections between what we're doing here in our virtual classroom and the real world outside of our virtual classroom. And then what I want to spend most of my time on today is starting in on Chapter 8 so that we don't lose today. Thank you for the private chat message. Exam 2 scores will be posted later today. They are ready to go, but I didn't want you guys distracted during class today, so I will be posting them later today. And you can stop by office hours if you have any questions about your scores. Okay, so what I want to do first, like I said, is to kind of draw out some of the things that we've been learning in the class here and some things out in real life in the chemical industry and also in biology land. So let's go ahead and do that. The molecule I have on the slide right here, the common name for this molecule is propylene. Think for a second to yourselves about what the IUPAC name is, because it's not propylene. Propylene is the common name here. So think to yourself about what the IUPAC name is. First, figure out how many carbon atoms there are in this chain here. So there are 3 atoms, so that means it's a base name of propane. Because we have a functional group that is an alkene, instead of calling it propane, we're going to call it propene. And in the case of propene, we don't actually have to designate a position of the double bonds because there's only one option. But if we were to designate it, it would be 1. So we would call this 1-propene or prop-1-ene. So propene, or propylene for its common name, is a very, very functional alkene. It's one of the simplest alkenes out there, the simplest beyond ethylene, which we've talked about a good bit. And I just want to point out all of the different things that we can do using propylene as a starting point. The first thing that we can do is we can take propylene and we can polymerize it, and that makes polypropylene. You guys, I'm sure, have heard of polypropylene. It's a very functional material used in a lot of fabrics, and it has a lot of different properties for, plastics and fabrics and things like that. We can also take propylene and we can add a molecule of water to this molecule of propylene. So we're going to add an OH on one side of the double bond and an H on the other side of the double bond. So overall, we've added a water molecule to the starting material. That gives us isopropyl alcohol, as in the same isopropyl alcohol that is rubbing alcohol, and as in the same isopropyl alcohol that is in most of your hand sanitizers. We can take our isopropyl alcohol and we can do an oxidation, what's called an oxidation on this molecule, to convert this hydroxyl group or alcohol group into a double bond called a ketone. And if we do that from isopropyl alcohol, we can get acetone. And acetone, if you're doing any organic chemistry lab, I'm sure you've met acetone in that setting before. It is a very common organic solvent. It is also something that used to be in nail polish removers and now has mostly been removed from nail polish removers. Okay, so here's a couple of different uses for propylene. We can also take propylene and we can oxidize it a different way to create this 3-membered ring called an epoxide ring. That gives us propylene oxide, which has a lot of functionality and a lot of different uses in industry. We can take propylene oxide and add a water molecule to that. So if we add an OH on one side and a hydrogen atom on the other side, we get propylene glycol, which is indeed an antifreeze. And so look at all of the functionality and different, very simple molecules, but very functional molecules, each with a different purpose, that we can get by taking an alkene starting material and doing all of these different conversions to it. And this is actually, this reaction in particular, this central one here is one that we're going to talk about in chapter 8. Chapter 8 focuses on the reactions of alkenes. And so we'll get into that in a little bit. But before we do, I just want to also give you a little flavor of alkenes in biology and draw together some of the fundamental work we're doing here with real life situations. So this slide should look familiar to you guys. It's a slide I showed you at the beginning of chapter 7 when we first started talking about alkenes. We talked about beta carotene, which is a major nutrient in carrots and a lot of other fruits and vegetables. We talked also about amphotericin B, this antifungal drug, and how both of these molecules have these alkenes or double bonds in kind of alternating positions. And those, that kind of organization of multiple double bonds gives them special properties. And we talked a little bit when we first started chapter 7 about how beta carotene is a vitamin A precursor and actually useful in eyesight. It's a nutrient that helps contribute to healthy eyesight. And so I wanted to show you how and why that is. So here is beta carotene. This is the natural product that you actually ingest from your food sources. In your body, beta carotene is converted into vitamin A, which is also called retinol. And this retinol, you can see, is kind of half of a beta carotene molecule. So actually each half of beta carotene becomes a retinol molecule through a bunch of steps. And we still have a lot of our double bonds here, but we've just modified kind of the tail end of it. Retinol gets modified further and ends up being covalently attached to a protein called opsin to be able to give you a kind of a protein small molecule conjugate called rhodopsin, which is a protein that's in the rods of your eyes. And so you can see this is a covalent attachment to a protein that's basically retinol or vitamin A that's been converted on this end and attached to a protein. But all of these double bonds are still in place from half of our beta carotene molecule. So how does this work to help with our vision? It goes like this. In your eye, there are things called rods and cones. Those are two different types of cells in your eyes that help us to perceive vision. And in the rod type of cells, they're along a long chain here, there are discs. And these discs have these protein molecules called rhodopsin embedded in the discs. So what rhodopsin looks like, we're going to zoom in and look on one of these rhodopsin protein small molecule conjugates. We are going to take our protein and we're going to covalently attach cis retinol. So here's cis retinol, and it's being represented by this little shape in pink that looks like a key. This retinol, cis retinol, is covalently attached to the protein to give us rhodopsin. And it is specifically the cis version at this position right here that is attached to the protein. Now, when a photon hits your eye, that photon has exactly the perfect amount of energy to convert this cis bond to a trans bond in the middle of retinol. So note that it's the only cis bond in retinol, and then after light hits it, all of the bonds are trans bonds. So what that means, because without that energy from the photon, we do not have free rotation or free conversion of the pi bonds, right? Without that energy from the photon, we cannot convert cis to trans. But when the photon comes in, that energy from the photon essentially breaks this pi bond, allows the molecule to rotate to the lower energy conformation, and then the pi bond reforms. And this conversion makes this bent version of cis-retinol conform and become this trans-retinol, all trans-retinol, which is kind of more of a straight line. And you can see that conformational change not only in the small molecule, but it causes a conformational change in the protein as well. And it's that protein conformational change that is registered back to your brain as a signal that a whole collection of these changes at the same time is how you perceive vision. So what happens to help complete the cycle is that this trans-retinol is then released from the protein. There's an enzyme that converts it back to the cis form, which takes a little bit of energy because the cis form is higher in energy. So there's an enzyme that uses a molecule of ATP, which is the energy currency for biology, to convert our trans-retinol back to cis-retinol so that it can join up with the protein again and go back through this cycle. So look at all these fundamental concepts that we have going on in organic chemistry that are now pertinent and relevant in something as everyday as your vision. Pretty cool, huh? So I'm not going to say too much more. This little segment here for the first part of class, everything that I've shown you so far, I am not going to test or quiz you on these topics. These are just to make this course more relevant and more interesting for your daily lives. But what I might do, for example, is show you a molecule of retinol and say, hey, well, you need to tell me what all of these bonds are, whether they're an E or a Z configuration. That would be a fundamental chemistry question that I might ask you relevant to these types of topics, but I'm not going to ask you to redraw the rhodopsin cycle or anything like that on a test or quiz, like the one you have coming up on Friday. Okay, so that covers I had planned those slides for the tail end of chapter 7 and we didn't quite make it on Monday. So they provided a nice segue actually for us between chapter 7 and chapter 8. And the rest of the class, we're gonna move on and talk about chapter 8 concepts. Now, chapter 8 is not going to be on your quiz on Friday. It's not gonna be on your quiz on Friday. It'll be on the next quiz though. But the concepts that we're going to talk about today for chapter 8, which is about alkene reactivity or the reactions of alkenes, some of the concepts from today's class are going to reinforce concepts from chapter 7. So you're not going to like lose your mental mojo moving into Friday. We're still going to be thinking about the same types of things that'll be relevant to your chapter 7 in the quiz. All right, so let's get started with chapter 8, which again is reactions of alkenes. So to set the stage for this, we talked in chapter 7 about making alkenes, right? Chapter 7 was called structure and synthesis of alkenes. And we talked about ways that we can now do this. We can make alkenes starting from alkyl halides. We also know how to start from alcohols using elimination reactions. And we learned about the E1 reaction, which is unimolecular, and the E2 reaction, which is bimolecular. Both of those elimination reactions overall look something like this, where you have a molecule that has a leaving group and another component, usually a hydrogen. And we're going to remove those two components and their sigma bonds. And we're going to create a pi bond and then a sigma bond between those two components. So this is called an elimination because we can say we are eliminating a molecule of XY, in this case, from our starting material to create a double bond. So both E1 and E2 follow the same overall formula, but of course their mechanisms are different. And so there are different stereochemical consequences and energetic consequences to their mechanisms. In chapter 8, what we're going to do now that we know how to make alkenes is focus on what we can do with them. What are the reactions of alkenes? And many of the reactions of alkenes can be described as what's called addition reactions, where we take a double bond and we take a molecule, for example, XY, and we add XY across that double bond so that the X half is attached to one side of the double bond and the Y half is attached to the other side of the double bond. So overall, we're going to be using our pi electrons from our alkene starting material and the sigma electrons from our other reaction partner to create two new sigma bonds. And if you look closely, you can see that these addition reactions are the reverse of these elimination reactions, right? And we can call these addition reactions, the terminology of the way that we say this as chemists is that we are going to add XY across a double bond. Just like up here, we said we're going to eliminate XY from this molecule to create a double bond. So I do want to point out, we can see from these overall reactions that addition seems to be the reverse of elimination. And overall, there are many cases where that will be true for an overall reaction. But mechanistically, this can be true where exactly every step of the electron flow to get from here to here can be done in reverse exactly based on electron flow to go from here to here, but not always. So there are going to be some examples where mechanistically the reverse goes through a completely different pathway. And we'll go through each of these step by step as we go through the chapter. Okay, in terms of thinking about the reactivity of alkenes, we're going to go back and review some things from chapter 7 about the structure of alkenes. So if you think about what you know about the structure of alkenes, you know that all 6 of the atoms here, the 2 carbons involved in the double bond, and then each of their 2 substituents, so that's 6 atoms, are all in the same plane as each other. They're forced into that configuration by the constraints of sp2 centers, which are trigonal planar, and the p orbitals that are left over unhybridized that have to overlap with each other. And so these 6 atoms are all in the same plane as each other for every single double bond, no matter what the double bond is. In the case of how I've drawn this, those 6 atoms are all perpendicular to the plane of your screen. We also have our pi bond, which exists above and below that plane of the 6 atoms, right? Half of it is above and half of it is below. So what else do we know about double bonds? Well, double bonds are made up of a sigma bond, 2 electrons shared between the 2 carbon atoms in orbitals that are hybridized and pointed towards each other in a direct overlap. That's a strong bond because it's a direct overlap. They're also made up of, in addition to 1 sigma bond, 1 pi bond, which again is half above and half below the plane of the 6 atoms. And that pi bond is not as strong as the sigma bond, right? So the electrons in the pi bond are not held as tightly. This should make sense to you intuitively with how those electrons are oriented relative to the positively charged nuclei that are holding them there, right? They're kind of on the outskirts, right? As opposed to the electrons that are in the sigma bond, which are kind of trapped between the 2 carbon nuclei. So our pi bond electrons are held a lot less tightly, right? And so they're more reactive. And most of our reactivity that we're going to see in chapter 8 involves taking the pi electrons from our alkenes and destroying that pi bond to make 2 new sigma bonds. We can use the 2 electrons from our pi bond and then 2 electrons from whatever our other reactant is coming in to be able to do that. So we're going to exchange out 1 pi bond for 2 sigma bonds. Okay, and so that means if you think about that also in terms of delta H for reactions, we're going to be trading a pi bond for a sigma bond, and that's going to favor the product. So these are typically going to be exothermic reactions. Here is the very most generic form of what I can describe for much of what we will see in chapter 8. Not everything, but much of what we will see in chapter 8. We have a pi bond, right? And that pi bond has these 2 electrons, which again are loosely held. Those 2 electrons represent an area of electron density, which means those 2 electrons can act in a nucleophilic manner. And in fact, that's often what happens, where you have an electrophile nearby, and the 2 electrons from that pi bond can reach out and attack that electrophile, forming a new sigma bond with the electrophile using the electrons that were in the pi bond. Now think about what you did to that pi bond. Well, that pi bond was two p orbitals that were parallel with each other. If you took, and they were sharing one pair of electrons, right? They were sharing those electrons. So if you take those two electrons and you give them only to one side of the pi bond, you create a new sigma bond. So we rehybridize the carbon center. So now we've got an sp3 center instead of an sp2 center and a new sigma bond. But what did you leave behind? You left behind the other p orbital that had been sharing that electron set and now is just empty. So that is a carbocation, right? So we have a carbocation left behind. And so just like in a lot of the other reactions we've seen, E1, SN1, we are going to have carbocations as free intermediates in a lot of the reactions we see in chapter 8. And so that means that if you don't have carbocation stability trends down, you need to get those down like now. More substituted carbocations are more stable. So a tertiary carbocation is more stable than a secondary is more stable than a primary. A methyl carbocation is not stable at all. Also, don't forget about allylic carbocation. So if you put your carbocation next to a double bond, then the resonance stabilization helps that carbocation to be even more stable. Okay, so here's our big overview of the fundamental concepts we're going to be applying. Now we're going to look at a generic mechanism for some, not all, but some of the reactions that we're going to see in chapter 8. And what we're going to call some of these reactions is electrophilic addition. So if we don't know of any other pathway that our molecules are going to undergo and it's a double bond, electrophilic addition should be your best guess. This is going to be the default setting for how alkenes react. In that first step, like I showed you on the last slide, our pi bond electrons, which can be nucleophilic, are going to reach out and form a new sigma bond with your electrophile. And that will leave behind a carbocation on the other carbon of the double bond. And that, because we know how our carbocation stability trends work, we can help predict patterns in our product formation based on this carbocation stability. So the carbocation that's going to be left behind will be the more substituted carbon of the two from your double bond. In our second step, and we'll talk about that over the next couple of slides. In this example, we don't have a way of differentiating, but I'll show you some examples where we do have a way of differentiating in the next couple of slides. In our second step, our nucleophile can attack our carbocation, right? So we have a reactive intermediate here, a carbocation. And if we have any nucleophile, it can be a strong one or a weak one, it doesn't matter. Any nucleophile can attack our carbocation. And that'll form our next sigma bond. So remember, overall, we're taking a pi bond away and we're forming two sigma bonds. One of them is going to be formed using the electrons of the pi bond. The other is going to be formed using electrons that are coming in from whatever that second reagent is. These will be all more clear once we have some specific examples to look at. But another couple of things that I want to make kind of a key point of is that these pink arrows here are mechanistic arrows, and they are still, as they always do, they are still showing you how the electrons are moving. So they're going from high density electron areas, the nucleophilic sites, and they're pointing to the electrophilic sites, which are low electron density sites. So I've said that a couple of times now that these types of electrophilic addition reactions are going to be the most common reactions that alkenes do. They are not the only ones, and so we will see a lot more types throughout the course of chapter 8, but we'll probably won't get to those until next week. I want to take a moment and let you guys kind of ponder for a second just the name electrophilic addition. So just like we talked about with enantiomeric excess in chapter 5, these words, electrophilic addition, they mean something and they can tell you something, right? Electrophilic addition means you are adding an electrophile to a double bond, right? Electrophilic addition of an alkene means you are adding an electrophile to that alkene. So even though we can say electrophilic addition, we're adding the electrophile to the alkene, don't forget that your electron arrows still have to show the pi bond attacking that electrophile. All right. Let's look at some specific examples. So I don't know if I'll have time to do both addition of HX and hydration today, but we'll for sure get through addition of HX. But I put the whole list up here of different types of addition to alkenes. We certainly won't get to these ones that are grayed out. I know we don't have time for that. But I wanted to have them in our kind of outline here so that you can start making a connection between these different types of reactions and the notion that all of these types of reactions, there's 5 different ones listed here, they are all different versions of addition to alkenes. And so we've talked about addition to alkenes as a broad category in generic terms, and now we're going to touch on each one of these examples in specific terms, but they're all going to follow what we've already kind of been talking about. Let's get started. Addition of HX. So HX is a hydrogen halide, right? X is a most common way that organic chemists designate a halogen. So when we say we're going to do addition of HX, we are literally going to be adding HBr or HCl or HI or HF, is that the one I forgot? Across a double bond, right? And this is exactly the reverse of alkyl halide elimination. Let me say that again. This reaction that I'm going to be talking about for most of the rest of class today is exactly and perfectly the reverse of an E1 alkyl halide elimination. So it's the same concepts, the same intermediates, just in reverse. And so let's see what that looks like. In our first mechanistic step, we are going to have our nucleophilic pi bond electrons attack our electrophilic H from HBr. So why is this hydrogen atom electrophilic, you might ask? Well, it is because of the dipole, this very strong dipole of HBr. So our H is actually delta positive, if not freely an H plus, and our Br is very strongly delta negative. So our pi electrons can reach out and protonate themselves, leaving behind a Br minus and a protonated intermediate. So when we are doing this, we're taking our pi bond electrons, reaching out and forming a new sigma bond with the proton from HBr, using those pi electrons, leaving behind a carbocation on the other carbon of the double bond. Now we have this carbocation intermediate. Well, that's a pretty high energy intermediate, right? Because it's a carbocation. And we've just generated Br minus. Br minus is a good nucleophile, right? It's not a good base, it's a weak base, but it's a good nucleophile. So in our second step, the nucleophile that we just generated in the first step can reach over and attack our carbocation high energy intermediate, forming a new sigma bond using the 2 electrons on, like from a lone pair on bromide, which actually are the 2 electrons that used to be in a sigma bond on the starting material. So we formed our second new sigma bond here. It's a carbon halogen bond. All right, so hopefully you guys can see this is exactly the reverse, mechanistically exactly the reverse of an E1 elimination. If we go backwards in our E1 elimination, we will first break this carbon halogen bond with the electrons going to the bromine to give a carbocation intermediate. Looks like this. And then our carbocation intermediate could be deprotonated by a base, which would take the 2 electrons from the sigma bond and form a new pi bond using the empty p orbital next door. So this is mechanistically exactly an E1 elimination in reverse every single step of the way. Okay, so we have a question in the chat box. Will a pi bond ever outcompete the halide as a nucleophile? That is a great question. Okay, so the question is, you have this intermediate, which is a carbocation intermediate. We've talked about this halogen being a nucleophile and attacking that double bond. But if you have a bunch of more of your starting material, the pi bond electrons here are also nucleophilic and can indeed attack at that position. So that's a little bit subtle and a little bit to the side of where we're at right now. That's a gray area, I would say, in organic chemistry. But there are reactions that we could set up if we choose our conditions the right way so that we favor what would end up being a polymerization of this molecule. So if you remember all the way back at the first slide, I talked about the polymerization of propylene to become polypropylene. In that case, we're doing something exactly like this. What I'm talking about now is a little outside of the scope of where we're at right now. So for practical purposes, I want everyone just to focus on HX addition, because that's what we're defining this reaction as being for right now, right? I'm telling you, in this case, HX addition is what's going to happen. But it's great to be thinking about other things that might or could happen, because in real life organic chemistry, that's a lot of what we have to deal with as chemists, is being able to predict and figure out what are the other unwanted side reactions that could be going on, and how do we choose our conditions or choose our substrates or choose our reagents so that we stop those unwanted side reactions and favor the pathway that we want. This is like 3 levels up from where we're at right now. So for today, we just want to think about HX addition, where we're going to protonate this pi bond, create a carbocation, and for HX addition, it is the X minus that acts as the nucleophile to form a new carbon X, or in this case, carbon bromide bond. Okay, thank you for the question though. All right, so note, we always have 2 different options for which carbon is going to get protonated, and then therefore which is the other carbon that's going to get the carbocation, right? We put it on the carbon on the left, the proton, which gave the carbocation position to the carbon on the right, but we could have protonated it the opposite way, so our proton went on the carbon on the right and our carbocation went on the carbon on the left. In this example, there's no difference because they're equivalent, right? There's no difference, and you would get a 50-50 mixture statistically. But that's not always going to be the case. And so how do we know if one side of this double bond is different than the other side of the double bond? How do we know which way it's going to go? And we have a rule for that, but we don't even need to get to the rule yet. Let's just think about it intuitively and using our fundamental knowledge of chemistry that we already know. I've given you a different substrate here. On one side of the double bond, we have 2 methyl groups. On the other side, we have a hydrogen atom and a methyl group, but these are the same substrate. In the top pathway, we're going to protonate the carbon on the right, forming a new sigma bond on the carbon on the right, leaving behind a carbocation on your carbon on your left. In the bottom pathway, we're going to do the opposite. We're going to protonate the carbon on the left and leave behind a carbocation on the carbon on the right. So in the top pathway, the carbocation we get is a tertiary carbocation. In the bottom pathway, the carbocation that we get is a secondary carbocation. And so our carbocation stability trends tell us that this tertiary carbocation is the favored intermediate. And indeed, this top pathway is the pathway that happens and not the bottom pathway. So because organic chemistry is organic chemistry and organic chemists are organic chemists, we have this really crazy rule that uses words to say what we just figured out on our own intuitively using the fundamentals that we already know. So we have a rule called Markovnikov's rule. Actually, before I let you guys read that, I'm going to say a word about Markovnikov's rule. Markovnikov's rule is a term that chemists use that you have to know and understand what it means. I could ask you a question like, here's an addition reaction. Tell me the Markovnikov product of this addition reaction. Or tell me the anti-Markovnikov product of this reaction. So Markovnikov's rule is a rule we need to know because of the culture of chemistry, the culture of organic chemistry, and because people talk about this in such a way that everybody knows what it means. Just like everybody knows the Kahn-Ingold-Prelog priorities mean a specific thing, Markovnikov's rule means the specific thing that we've just talked about. So let me read you the rule. The rule literally and actually says, Markovnikov's rule, is that the addition of a proton to the double bond of an alkene results in a product where that acidic proton is bonded to the carbon atom that already has the greater number of hydrogens. So that is how Markovnikov stated his rule. But if you think about what this means, and if you break it down according to what we just talked about using fundamentals, all that Markovnikov said was that your proton is going to go onto the less substituted carbon, right? Because the carbon that holds the more hydrogen atoms is the less substituted one. So your proton is going to go on the less substituted side so that your carbocation can be the more substituted side. So Markovnikov's rule is long and it has a lot of words, but it literally just means carbocation stability dictates which way you're going to go here. All right, so we can also extend Markovnikov's rule, which I'm going to go ahead and do right now to draw this distinction. Markovnikov himself only talked about adding a proton to a double bond, but we can apply this same concept to all of our electrophilic addition reactions. You guys haven't seen other versions yet, but we will see versions where it's not just HX we're adding, and in fact, there's no proton involved at all. And so what the extended version says is that instead of just referring to a proton, we can now refer generically to the electrophile, right? So in this case of HX addition, the electrophile is a proton. But if we were adding something different that wasn't HX, whatever the electrophile is, the electrophile will add in the way to generate the most stable intermediate, right? So this extended Markovnikov's rule is the one that I like better because it's more generic, and it's actually not really a rule at all. It's just saying, hey, the fundamental idea that you're going to generate the most stable intermediate is going to stay true, and it's going to hold true, right? So these Markovnikov's rule basically tell us that the electrophile, whatever the electrophile is, ends up on the less substituted carbon. Okay, so let's see some more examples. Oh, actually, before we see some examples, let's look at an energy diagram. So this energy diagram just gives us another way of rationalizing the experimentally observed Markovnikov product, right? We have an alkene starting material. We can add the HBr across in one direction or the other direction. And actually those two products have very similar energetics, right? The thermodynamics of those two products are similar because they both have the same number and type of sigma bonds as each other, right? They're constitutional isomers, but overall their thermodynamics, the energetics of those products are the same. But this one, the green pathway product, is favored because it goes through an intermediate that is more stable than the intermediate of the blue pathway. So in the example I'm showing you now, it's a different example than the other slide, but we would be creating a secondary carbocation if we add to one side versus a primary carbocation if we add our proton to the other side. And so, of course, the secondary carbocation is more stable, and that lower energy intermediate means also a lower transition state energy on that pathway. And that is why we get the Markovnikov product as the favored product, because of the stability of this intermediate in the pathway. Okay. All right, so let's look at some examples. So here is a pi bond, and we're going to do our Markovnikov addition of HX. So take a moment and think for yourself on your own, which side of the double bond would the proton add to? You're going to form a new sigma bond using these pi electrons in this first step. We're going to release a Br minus, but don't worry about that for now. Just think about the first step. Our pi bond electrons are going to form a new bond, a new sigma bond with a proton. Is that sigma bond going to be on the top carbon of the double bond or the bottom carbon of the double bond? So think about that for yourself for just a moment. Okay. Hopefully you guys all came to the right conclusion that that proton is going to add to the bottom carbon of the double bond. That will be a situation where you leave behind a carbocation at the top carbon, which would be a tertiary carbocation. Whereas if you do it the opposite way, where you put your proton on the top carbon, you're going to leave behind a secondary carbocation, and that is not as stable. So it is this top carbocation that forms, not the bottom one. That's why there's an X through that arrow. And it's this top carbocation that can then go on and be attacked by the nucleophilic bromide that we just released to form our new our second new sigma bond using these electrons, which are in green because they started out with our green HBr molecule, right? So we formed two new sigma bonds, one sigma bond using the electrons from the pi bond, the other sigma bond using the electrons from HBr. Okay, so there's a question in the chat box. It says, if we think in our minds of where the carbocation is more likely to go, will this work in every situation? Because that's how I was thinking of it for the addition of HX. Yes, this is actually Markovnikov's extended rule. If you are going to go through a carbocation intermediate, whichever carbocation is more likely to be, whichever carbocation is more stable is the one that is going to be more likely to be generated. And so that is how this will work for HX. Yes, exactly right. Okay, so let's see another couple of examples. We have a double bond in the middle of a kind of a carbon chain, right? And if we want to add HCl, so we don't always have to add HBr, we can add HCl across this double bond, right? And if we do that, then the carbocation would go on the more substituted side, which is the left-hand side, how I've drawn it. So that is where our chlorine would end up. Remember, if we're going to end up adding a Cl minus, that Cl minus is going to be the nucleophile that attacks our carbocation. All right, here's another one. We have a double bond in a ring. We're looking at forming either a tertiary carbocation on the left or a secondary carbocation on the right. So we'll prefer to add our tertiary carbocation, create our tertiary carbocation, and so that is where the chlorine atom will end up. So these are all Markovnikov orientations, or the Markovnikov products of these reactions. Here's another example, in this case HI. We have our double bond, which would make a tertiary carbocation on one side or a primary one on the other. So our tertiary carbocation would be favored, and so our tertiary carbocation spot is where our I minus would go in the second step of this reaction. So all of these are Markovnikov orientation products. So before I get to that question, I want to point out that this slide is an awesome slide to use as practice problems. You guys can go and draw your carbocation possibilities. You can do the mechanisms of these reactions. And you know what else you can do is you can actually use this slide as practice for your chapter 7 quiz coming on Friday, because you can take these molecules and try to do the elimination reactions of them, right? Okay, so we've been talking about adding HX using Markovnikov orientation. And when we do that, we put the X, right, because it was an X minus at some point, on the more substituted carbon. And that's what we've seen in all of these cases here. But we're synthetic chemists, and sometimes we have a target molecule in our minds that we need to make. We can't just make whatever we get. What if we want to make the other way around? What if we want to generate the anti-Markovnikov orientation? So in order to be able to do this, we have a new set of reagents that we have to use. So we as chemists, let me back up a little bit. In order to do this anti-Markovnikov orientation, we as chemists have to understand what's happening in our reaction flask. And we have to figure out how to kind of co-opt the fundamental rules, which we can't change. We can't change any fundamental rules. But what we can do is get creative and co-opt those fundamental rules and use them to our advantage. So if we want to do HX addition, but get the anti-Markovnikov orientation, here's how we're going to do it. We're still going to use HBr, but this time we're going to add another reagent to the mixture called a peroxide. And what that is going to do is, instead of going through a carbocation intermediate, we're now going to have a radical mechanism. And this radical mechanism ends up with the opposite stereochemistry, the opposite regiochemistry, I should say. And I'll show you how and why. Before I show you, I want to note that only HBr has the right thermodynamics to be able to do this reaction. So you can't do this reaction with HCl or HI. You have to use HBr to do this reaction. Okay, this is going to be a free radical chain reaction, which means that it is going to look very similar to the free radical chain reactions you guys already know from chapter 4 for the radical halogenation of alkanes, and from chapter 6 for the generation of alkyl halides using allylic radical halogenation. There's a couple of differences though, so let's go through it. In our initiation step, I told you we're going to need to add peroxides. That's the key ingredient to get anti-Markovnikov addition. We're going to add peroxide in addition to our HBr. And peroxides are any molecule that has this oxygen-oxygen single bond in it. This is a very weak bond. So with a little bit of heat, we can break this bond in half where one electron goes with each side. And so we're going to make two, for every molecule of peroxide, we're going to make 2 molecules of a peroxide radical, right? An oxygen-based radical. That oxygen-based radical is a very high energy intermediate, and it can abstract a hydrogen atom from HBr. Okay, so we're using the same HBr reagent that we used for our electrophilic addition on the previous slides. We're going to use that here. We're just going to use it with peroxides. So now our oxygen-hydrogen bond is going to be made using our radical from the oxygen and one of the 2 electrons of our HBr. And that's going to leave behind Br radical because we've broken our HBr bond homolytically, where one electron goes to form the new OH bond, the other electron goes with bromine radical. Okay, so these are our initiation steps, and overall in our initiation steps, we've generated a bromine radical. So now we have propagation steps just like before, and in our first propagation step, we can take our bromine radical and our substrate, and this time what we're going to do is take our pi bond electrons and we're going to split those. Remember, those are loosely held. So one of our pi bond electrons will go with a carbon atom to be a carbon-based radical. The other of our pi electrons will join up with the free radical of the bromine to create a new sigma bond. And you can see this because of the mechanistic arrows that I'm showing here, which just like up here, are showing single electron motions because they have half arrowheads. Okay, so what did we just do? We made a new carbon-bromine bond using 1 electron from the pi bond and 1 electron from the bromine radical. But we also generated a carbon-based radical. Now I want to remind everybody, carbon-based radicals have the same stability trend as carbocations. Let me say that again. Carbon-based radicals have the same stability trends as carbocations. So the more substituted carbon-based radical is the one that we generated here in this example, right? I've only showed you one orientation of this step of this carbon-bromine bond addition because this is the only radical that's formed where the radical is on the more substituted carbon. That was the first propagation step. In the second propagation step, our radical from our carbon atom forms a new sigma bond using one of the electrons of a new molecule of HBr. So we're breaking HBr homolytically again to create a new sigma bond using 1 electron from our radical and 1 electron from our HBr. So our hydrogen atom is being abstracted, a proton with 1 electron. And our bromine radical will be released, our bromine atom with 1 electron. So we just regenerated a bromine radical, which can now go back and find a new molecule of starting material and start the process all over again, because this is a radical chain reaction, just like chapter 4, just like chapter 6, radical chain reaction. Okay, here's the cool part. This radical that we've formed, the more stable radical is still the more substituted radical, right? So I told you there are 2 different options. We could add this way, or we could add this way, but this way does not happen because this way gives us the tertiary radical, which is more stable. So free radical addition of HX ends up where you get the X on the less substituted carbon. So what you end up with is an apparent, what's called anti-Markovnikov orientation. We're still forming the same most stable intermediate. We are still using our fundamental chemistry to say, how do we make a stable intermediate? What is the intermediate and what's it going to be that's the most stable? And I just want to kind of drive this point home and really draw it out and say that because in this reaction, in the free radical HBr addition reaction, X is what's added first. X is what's added first. So your carbon-based radical intermediate is going to be a more substituted carbon-based radical. X is added first. But when we did our electrophilic HX addition, H was added first. You left behind a carbocation that was the most substituted carbocation, just like this is the most substituted radical. So if we understand how these reactions occur in a mechanistic way, we will get to the right product, the right orientation, but we have to understand how they work. Okay, so I was going to give you guys an in-class participation, but class is over already. So what I'm gonna do instead is post this in-class participation so you guys can kind of muddle through it on your own. And I would like for you guys to upload this for a participation, but I won't make it due today. I'll make it due like after the next class or something like that, but I will post it so you guys can practice and look at these things. And yours will be due probably at the end of the day on Friday. Okay, and that's it for today. So thank you guys for your attention, and I can answer questions if you guys have them.
Thank you. Have a wonderful day.
Thank you, you too. Okay, if there are no questions, then I will let you guys go. Hope everyone has a great day. See you on Friday.